And thank you for this invitation to give this talk to you online. So I'm going to talk about LC3, which is a really practical way we can reduce CO2 emissions associated with cementitious materials, both fast and at scale. And these are really the two things we need if we're going to confront climate change. So what's the context of this? The context of this is that materials based on cement make up more than all other materials put together. It's purely for this reason that they account for such a high proportion of world CO2 emissions. As you can see on this graph at top right, that the embodied CO2 in terms of kilo per kilo is some of the lowest of all materials. So we're not going to improve from a CO2 perspective by replacing cement with other materials, and we simply don't have enough resources for other materials. So if we take the example of timber here, this is currently about 8% of the supply of concrete, and this is already on the limit of sustainability. We're cutting down more trees than we're planting. It's been estimated that to replace just 1/4 of cementitious materials with timber, we'd have to plant new forests 1.5 times the size of India. So Portland cements are an inevitable consequence of the chemistry and geology of the earth. We see here that just 8 elements make up more than 98% of the composition of the earth. That's oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. Now, the alkalis are basically too soluble. On the other hand, iron and magnesium oxide have too low solubility. So this means going from the whole composition of the earth, we come to a system of just 3 oxides, calcium, silica, and alumina, which we've studied for over 100 years. And we know in this system, there are basically only 2 regions where we can produce cementitious materials. The regions of the calcium silicate, which is what we call Portland cement, and this region where we have calcium aluminate, calcium sulfoaluminate. At first sight, this looks interesting because it contains less calcium, so less CO2, but the problem is we don't have the minerals we need, which contain much more alumina compared to silica. We'd have to use things like bauxite, which is heavily in demand to produce aluminium. So Portland cements are here to stay, and the best way to reduce CO2 is to replace as much as possible of the Portland cement with other materials. Now, this is not new. We've been using substitute materials, particularly slag and fly ash, for many, many years. The problem is that the amounts of slag and fly ash available today are really quite limited, and these will decrease drastically in the future. Because the first thing we've got to do to confront climate change is to avoid burning coal. And producing iron from iron ore is also a very carbon-intensive process. So we don't have a lot of other materials available. Things like vegetable ashes are only available in very small amounts. We have a lot of limestone, but when we can't use that in additions more than 10–15%. What can be a real game changer here is our clays, which when they're calcined, that's to say heated to about 800 degrees, produce very reactive materials. So this is behind our invention of LC3, to realize that SCMs are the best solution for the sustainable future, that the only material we have in viable quantities is calcined clay. And this is the really new novelty, that we realize that there's this synergetic reaction between calcined clay and limestone that allows very high levels of substitution. So this was a project we christened LC3 and has been a project supported by the Swiss government since 2013. Now, the reason we get this much lower CO2 is because we place the clinker, which has very high emissions, we have a small amount of clinker we still have, but the calcined clay has much, much lower emissions, maybe only 1/10 of the emissions of clinker. And the other ingredients, the limestone and the gypsum, basically have near zero CO2 emissions. But in terms of performance, we can get the same or even better mechanical strength as the reference Portland cement. In only 7 days, with this mixture made in the lab, we can catch up or overtake the strength of the Portland cement, and we can even produce similar strengths at very early ages, like 1 day, if we optimize the grinding. So in summary, we've got 50% less clinker, 40% less CO2, with a similar strength, and some properties like chloride resistance, resistance to alkali silica reaction are much improved. Now, the first question is, what kinds of clay are suitable? We need to have some of this mineral kaolinite. This is a 1-to-1 clay, which has layers of silica and alumina. And when it's calcined, this structure becomes disrupted, and both the silica and the alumina are available to react and form hydrates. But we don't need high-grade metakaolin. We only need clays which are often available as wastes, which contain a much lower amount of kaolin. And we can see in terms of strength development that the red lines indicate the reference strength of the pure Portland cement. So at, say, 7 days, you can get the same strength of the Portland cement with a kaolinite content around 30 to 50%. If you have higher contents, well, you can just dilute it with more limestone. Even lower contents can work out well because you can enrich them by separation. But the important point here is these kind of low-grade kaolins are not documented in official reserves. The amounts available are many orders of magnitude more than high-grade kaolin for ceramic applications. And we can get an idea of the distribution by looking at these maps, because everywhere in either of these maps you see this orange-yellow color, you will have clays containing kaolin. And you can see in China, they're almost everywhere, apart from really maybe the very far north. Now, once you've got the clay, you have to process it and then calcine it. And then you can go in 2 directions. Either you can take the calcined clay and blend with the clinker and the limestone and the gypsum all together to give you what we call LC3, or you can produce a separate product, which is just the calcined clay, the limestone, and the gypsum, which is what we call LC2, and then blend that with OPC at the concrete level. Now, the calcination of the clay, more good news, it has to be done in the range of about 700 to 850. So there's quite a wide temperature region, which means the process is fairly straightforward. And we can use existing equipment. We can use rotary kilns, or we can use flash calciners. You can even retrofit existing kilns. We had a trial that took place fairly recently where only 6 hours after stopping producing clinker, they could already produce calcined clay. So if you've got excess capacity, probably the best thing you can do is convert some of your existing kilns to producing calcined clays. This is not just a nice idea in the lab. We've already taken it to full scale. First, we did this in Cuba, and here you can see the house we built in Cuba. These blocks are made from LC3, and also this render to coat the surface of the house is also made from LC3. And this could be used by the workers with no training, no noticeable difference with the existing product. This is the second house we built in India, and we could demonstrate that this could save over 14 tons of CO2, even compared to existing fly ash solutions. And here we have one of the first full-scale plants, which is set up in the Ivory Coast. Now, this plant in the Ivory Coast demonstrated another important criteria, which is the ability to control the color of the clay. So people are used to having gray cement, and for some people, the idea of having a kind of pink or red cement is not very nice. But with a very simple technology coming from the brick industry, you can make the clay gray. Just to touch on some of the key advantages, particularly chloride resistance, which is the #1 issue of durability of concrete. Here you can see the chloride penetration in the reference Portland cement. It's somewhat better with slag and better again with fly ash, but very best of all, is the calcine clay limestone combination, which has an apparent diffusion coefficient, which is 10 times less than the reference. There are questions about the workability, but good properties can be attained controlled by admixtures. New admixtures are now on the market, and the product has very good cohesion, so it makes it very suitable for self-compacting concrete. So what's the potential of this technology? Well, this graph here shows the average levels of substitution worldwide from the GCCA figures. And you can see this is stagnated at only around 20% for the past decade or so, due to the lack of availability of slag and fly ash. But if we remove that limitation, we can go to a clinker substitution level of at least 40%. And on a time scale of 2050, we could probably go higher than this. 40% substitution on average worldwide would represent a saving of 400 million tons of CO2 per year. And if we could go to 55, this would represent 800 million tons of CO2. That's really enormous. That's like 2% of all the CO2 emissions today with just one technology. Even better news, you can save money. You can really reduce the costs of LC3 compared to your OPC reference in both an integrated plant and also especially in a grinding plant. So we're very pleased to see that this has really been taken up around the world. We're now in contact with producers in more than 40 countries. And this slide here shows some of the plants either coming online in the next, either already there or coming online in the next 1 to 2 years. So you can really see this technology is taken off. It could be done in China, and I hope some people will really look at this more detail soon. Before finishing, I just want to say that, you know, this is only one part of the chain. And if we worked at all levels of more efficient clinker production, less clinker in cement, less cement in concrete, less concrete in buildings, we could potentially save about 80% of the emissions. Just looking at the cement in concrete, we see today there's tremendous dispersion, tremendous wastage. And one way this can be reduced is by going from site mixing to ready mix mixing. However, what we do not want to do is start concentrating on 3D printing, because this is a very inefficient way of making concrete, exactly the reverse of what we need to confront climate change. And these kind of multiple levers have been taken up by many people. This is the GCCA roadmaps, which shows the savings we can have in design and construction, in the production of concrete, in the cement and binders, and then small amount will have to come from carbon capture and storage. So to conclude, I hope I've managed to give you a small insight on how we can reduce CO2 emissions. We can work at the cement level by increasing SCM substitution. We can work at the concrete level by minimizing cement content, and we can also work at the structural level. All of these will generally lower cost, so very good news. We will never be able to produce pure, completely zero carbon concrete by these means. We'll always have a small residue that has to be dealt with by carbon capture and storage, but this has high costs and the infrastructure is not in place. So it's very important to look at all these other levers before we resort to carbon capture and storage. In terms of SCMs, calcine clays are really the only option to take this technology much further. And the good news is this can be done fast and at scale. So I'd like to thank you for your attention. Any students online may be interested in attending our doctoral school in February, and any other questions, please contact us at these various sites. Thank you very much.